Now let's talk about sampling distributions. A sampling distribution is the distribution of all possible values of a certain statistic when all possible samples of the same size are taken from the same population. We represent a sampling distribution just like we do any other probability distribution, sometimes in the format of a table or a probability histogram, or sometimes just by a formula. So again, sample means, sample variances, and sample proportions target the values of our population parameters. Now remember when we talked about probability distributions, we discussed how to find the expected value for a probability distribution. So notice here we have the expected value of x bar, in other words, the mean of the sample means. The expected value of x bar is just our population mean, mu. And when we look at the distribution of the sample means, it tends to be a normal distribution. For our next statistic, our variance, the expected value of the sample variance is just equal to the population variance. This distribution of the sample variances tends to be skewed to the right. And finally, our expected value for our sample proportion is just equal to the population proportion. And this one also tends to be a normal distribution. Here's an example of a sampling distribution. If we repeat this process, we roll a die 5 times, and we find the mean x bar, the variance s squared, and the proportion of odd numbers of each sample. What do we know about the behavior of all the sample means that we would get as we continue this process indefinitely? Well, here's what it would look like. Here's our procedure that we roll a die 5 times and we find the sample mean x bar. Now in this case, since we've got a fair die, all 6 outcomes are equally likely. So if we found the population mean, which would be the expected value of our original probability distribution, that would be 3.5. If we continue this process through 10,000 trials, here's one example of having done this. The mean turned out to be 3.49. And here's a graph of what the distribution looked like after the 10,000 trials. So notice it looks very much like a normal distribution. If we look at the variances for our 10,000 trials, our population variance for the original probability distribution would have been 2.9, and our sample variance turns out to be 2.88. And notice what this distribution looks like. It's skewed to the right. And finally, if we look at the proportions of odd numbers in each of our samples, since there are 3 odd numbers and 3 even numbers on the die, then our population proportion would be 0.5. For our 10,000 trials, the mean of our sample proportions turned out to be 0.5 also. And if we look at this distribution, it also looks like it's approximately normal. Here's another example. If we take a spinner that has 3 equal areas labeled 1, 2, and 3, we spin it twice, find the sample mean and the proportion of odd numbers of the results. Let's look at this and think about what possible samples we could get. For each spin there are 3 possibilities. So if we use the multiplication rule from probability, that means there are 9 possible samples. Here are the 9 possible samples that we could get. So here's spin 1 and spin 2. So here are our 9 samples. Then we can calculate the mean for each sample. And for this column, if we look at the proportion of odd numbers in the sample, for example, in this sample 1, 1, both numbers are odd. So our proportion is 2 out of 2, or 1. So our different possible proportions of odd numbers are either 1 or 0.5 or 0. If we look at the sampling distribution for the sample mean first, we would list all the different possible values for our sample mean. These are all the different values that came up from our 9 samples. The number of times each one occurred. So for example, the sample mean of 2 happened in 3 of those samples. Then since each of those samples was equally likely, then our probabilities are just 1/9 times the number of times that sample mean occurred. So here's our probability distribution for our sample mean. If we want to find the expected value for our sampling distribution, this is just like what we did in Chapter 5. Our expected value for this sampling distribution would be 2. Now if we think about the population mean for our original spinner, our 3 possible results were 1, 2, and 3. If we found the mean of those three, it would also be 2. The expected value for our sampling distribution and our population mean are the same value. Now if we look at the sampling distribution for the proportion of odd numbers, we're going to do the same thing. So here we have all the possible values of our sample proportion. So this is our random variable in this column. The number of times that each one occurred, so the frequency of each one of those values. And then again, since each of those 9 samples were equally likely, then our probabilities are just 1/9 times the frequency of each one of those sample proportions. In this case, the expected value of our sampling distribution turns out to be 2/3. And again, if we think about our original process using the spinner, 2 out of the 3 numbers were odd numbers. So the population mean for this would also be 2/3.